Alright, so we talked yesterday about ideal gases. And we wrote down two formulas. They give us the relationship between four quantities we use to describe an ideal gas. P is for pressure. V, almost revealed it now. V is for volume. Capital N is
force.
Right? Number of molecules, and T is temperature in the unit of Kelvin. And K is a constant known as the Boltzmann constant. I can write that one here. 1.38 times 10 to the power of minus 23. And what is the unit of this constant? Joules per Kelvin. Yes.
We have it.
Alright, what about this formula here? Still P is for pressure, V is for volume, T is for temperature. What is N? No, what do we mean by N? Not number of particles, but number of moles. Remember that 1 mole is equal to 6.022 times 10 to the power of 23 particles. So that's Avogadros number. So I write down N. Avogadros number 6.022 times 10 to the power of 3. So 1 mole is but it's this number of particles. And if we take small letter n, number of moles, if we take the number of particles and we divide it by Avogadros number, we get n. So basically what they've done here is they divided this with Avogadros number. And that means that the constant K has now changed to the constant R. So here the constant R is equal to, that's equal to 8.31 joules per Kelvin per moles. So that is referred to as the ideal gas law. That's an ideal gas law, as we use ideal gases in trying to understand how real gases behave. But of course, that's an idealized situation. So what assumption lies behind this ideal gas compared to real gases? Right? Yeah, no potential energy, or that's correct, no forces between the particle. That's correct. That means no forces between the particles. That would be the same as saying no potential energy.
Oh no, we're testing you now.
And no phase change. I mean, we press the ideal gas very close together. If it's the ideal gas, we'll assume that no phase changes will occur. It won't condense into liquid. All right. What other assumption lies behind the ideal gas, Lamia? There's no loss in energy. That means that, to be precise, there's no loss of energy during collisions. So the collisions are elastic. And Elastic collision is where the kinetic energy is the same before and after the collisions. That means that during those collisions there won't be any energy loss. And another one, does anyone have the third one I thought was important?
Obeys gas laws.
Yeah, obeys.
The gas laws. Or the ideal gas laws.
Yeah, but that was not an assumption I wrote.
So I wrote down.
Obeys the laws of mechanics. Yeah.
What does the last point mean?
Yeah, what does the last thing means that obeys the laws of mechanics? What does that mean? What do I mean by that?
It means you can treat them in the same way you can treat any other objects. So you can use velocity in terms of kinetic
Yeah.
kinetics.
So we describe the behavior of gas in terms of mechanical laws of mechanics, as compared to which other branches of physics would we have used to describe particles? Quantum physics, maybe, statistical mechanics, complicated stuff. So we kind of use the laws of mechanics to describe the behavior of the gas, not getting into more complicated models of versions of physics. And there are other assumptions. So basically what was seen on exam, you should mention 1 or 2 or maybe up to 3 assumption of the ideal gas. So these are kind of the assumption, and those assumptions, they are true if the density of the particle is low, the temperature is low, and the pressure is low. So it's these laws here, these assumptions, they are true for when there's great distance between the particles. It means a low density. Yeah.
It's just like, I don't know if this is the right question to ask, but how does it obey the laws of mechanics when there's no temperature, when there's no energy, no loss of energy? Don't you have loss of energy?
No, when we talk about collisions, right? So we talk about pressure, right?
Yeah.
So how do I describe pressure?
Like when they hit the, how many times?
Yeah, when they hit the container walls, when this particle hit the container wall, it will exert a force on the container. It will bounce back in an elastic collision. So these forces, they will then exert pressure. I use laws of mechanics to kind of describe the different these different quantities here. So that's kind of what I mean by obeys the laws of mechanics. I describe the features of the gas using laws of mechanics. All right, so that is the ideal gas law. And yeah.
What does it mean by there's no potential energy?
So we talked about it yesterday that I'm standing here on the 3rd floor.
Mm-hmm.
So I have potential energy due to my position in the gravitational field. But that kind of, the assumption is that there's a gravitational force exerted on me.
Mm-hmm.
If there wasn't a gravitational force
Mm-hmm.
between me and this earth,
Yeah.
then there wouldn't be potential energy. So no potential energy is actually is between those particles. If there were forces between them, in the real world there are in some gases attractive forces between the particles, then the gas would have some potential energy.
Okay.
But for an ideal gas, we assume potential energy to be 0.
These are ideal gas
Yeah,
assumptions.
yeah.
Okay.
Yeah, that's an ideal gas assumption. Real gases have potential energy.
Yeah, okay, perfect.
So when I want to find the internal energy of the gas, I know that. Does anyone remember the formula for the kinetic energy of one particle? It's 3 divided by 2 times Boltzmann constant times T. That is the formula for the average kinetic energy of each particle. So if I want to find the energy of all the particles, what do I do then? If I want to find the energy of all the particles, Emily.
You times all the energies and then you divide them by the amount of particles there.
If every particle, on average, each particle had this kinetic energy.
You do that by the times the amount of particles.
Yeah.
in the
And that's what number here is?
moles.
Moles or
Avogadros
Like
number.
N, yeah.
Yeah.
I take then 3 over 2 times N K T. That will then be the internal energy of that gas. But then I assume that the internal energy of the ideal gas is only due to their kinetic energy, assuming that the potential energy is 0.
Wait, are these formulas in the formula booklet? Or is one of them?
Is
one of them in the formula booklet?
Some of them, yeah. This one in the formula booklet. Not quite sure about this one.
Wait, could you also label what those formulas are? Like, what is that?
So what was this formula? I forgot.
Okay. The kinetic energy for a particle.
Yeah, average.
Okay, average.
That's important. Average.
Of all the particles in this gas?
Average kinetic energy per particle.
Oh.
So that's per particle. And this is internal energy of an ideal gas. So yeah, I would assume that this won't be in the data booklet, this will be in the data booklet, and more of this later. We will get to that later. And we also can remember that that's the ideal gas law. But then it's a question of how do we use this ideal gas law? And we are looking at another way of writing ideals. It's going to work with it, different ideal gas laws. But we're going to look at 3 kind of situation where we have to apply the ideal gas law. So let's say we start with an example that if we have a gas, so this is a gas where we have a fixed number of particles. So you have a fixed number of particles. And let's say we have a container, 4 walls in that container. That means what other quantity is fixed? Something else can change here. Volume. So the volume is also fixed volume. And let's say that I now start heating. Let's say the initial pressure is let's do 1 times 10 to the power of 5 Pascal. Is that a high pressure? It seems big. A pressure of 100,000. Is that a lot?
That's basically what we have at sea level.
Yeah, that's basically what we have here. We have here on the unit we had yesterday, we talked about atmospheric pressure. That's 1.0, I forgot 3 times 10 to the power of 5 Pascal. So that's what we have here. And let's say that the initial temperature let's say that's room temperature if I had 25 degrees to 273, I get 298. Kelvin. So then I start heating this gas. I have a heat supply and I start heating the gas. So temperature increases to, let's say I increase it to 400 Kelvin. A very common problem. I have fixed number of particles, fixed volume. I give you the initial pressure, the initial temperature. Something changes, the temperature changes, and then I need to find the new pressure. Determine the new pressure. The new value for the pressure. And in the book they gave you the names of these different laws. I don't really think, I think it was just use of the ideal gas law. But the idea, yeah.
Sorry, don't you just divide by the initial temperature and time by the time?
Yeah, so basically what we do is I like to kind of write this ideal gas law in a different way. I like to write it as, if I take the initial pressure times the initial volume divided with the initial number of particles or number of moles times the initial temperature, that will be the same if one of these size magnitudes and one of these quantities changes, so that's equal to the new pressure times the new volume times the new number of particles times the new temperature. This is another way we can write ideal gas law when we talk about something that changes. And if the number of particles is fixed and the volume is fixed, that means that this here is equal to this and this is equal to this. This general formula will then be simplified to pressure 1 divided with temperature 1. And that should be equal to the new pressure divided with the new temperature. So basically what I'm saying is that if I take, I probably didn't explain that too well, that if I look at this formula here, if I divide with N times T on both sides, I will get pressure times volume divided by number of particles times temperature. That will equal to K. And what is K? A constant. So if I take the pressure times the volume divided by number of particles times the temperature, that will always be a constant. So then we look at, this is the situation at one time, and this is the situation at another time. That has to be equal. But now I'm saying that we have fixed number of particles, we have fixed volume, so now I can simplify this into that. So how, yeah, it?
So even if you change the volume, or would that formula still apply?
Yeah, but then if I change the volume here, I will then if I change the volume here, I would have to have the volume in the formula. Yeah. So sometimes they present this as a law, but I think it's smart to just think of this and look at what's fixed and then simplify the equation. So I want to determine the pressure in situation 2, the new pressure. So I multiply with both sides with the new temperature divided by T2. So I have that pressure 2 is equal to pressure 1 times the temperature 2 divided by temperature 1. So just inserting numbers, that's 1.1 times 10 to the power of 5 times 400 divided with 298, and then we put that into the calculator and we calculate the new pressure. As the phrase ahead of me.
1.34.
1.34 times 10 to the power of 5 Pascal. Good. So these are types of problems you will get. Clearly stated what's fixed, what doesn't change, and then they describe a change and you have to find a new value for either temperature or pressure. So let's do one more example of this. Okay. I have a gas. Gas, you need to pay attention, right? A very idealized description. I have a piston. That's no friction against the container wall, but it's still sealed, so no particles escapes. But this piston here, Emily, this piston here is free to move. So I have inside this container, I have particles which are moving. So these particles, they are moving, bouncing around. And this one, if there were vacuum here, no gas, it will kind of fall down. So the gas is holding this one up. So the pressure inside the gas is constant, holding this piston up. So here we have fixed pressure. It's sealed. So what other things are fixed? If it's a sealed, yeah, number of particles.
Wait, I said volume.
Volume, okay, volume. Then you were wrong. Yeah,
Because is it because it's like it can move?
yeah, it can move.
So, but it's a fixed pressure, so it won't move. But it can move. The thing on the top.
Yeah, it's a fixed pressure. Well, let's describe it. I will explain it. So
then
now it's sealed. That means
That means that there's not fixed number of particles.
Yep.
And also it can move since the pressure can stay the same but the volume can change.
yeah, fixed number of particles. And let's say that initial volume let's keep that at 1.0 1 cubic meter, no, 1 cubic, no, what, 1 decimeter cubed. Initial temperature I call that, let's say we do 298 Kelvin. And we have here, oh yeah, I will try to say, so what I mean by fixed pressure, so this piston, it can slide up and down frictionlessly. It has a specific mass. So this mass is being pulled down by gravity, so there's a weight exerted on this piston. So this piston is being pressed down by its own weight. That means that it will apply a force because pressure, it will apply force, and that will apply pressure because pressure is a force divided by area. So if I take the surface area of this piston under it in 3 dimensions, take the force of gravity divided by that area, you find the pressure. If the mass of this piston doesn't change, the pressure is constant. Assuming there's no way for these walls to actually decrease in or increase in length or thickness or be pushed together. So this is a simple way, idealized way to describing how we can have a fixed pressure. So then we increase the temperature. So we increase the temperature to let's go crazy, let's do 500 Kelvin. So what will change now? If we increase the temperature now, in this situation, what quantity will change and how will it change? Isha?
Oh, no. I'm just doing it, like solving it. I don't have my hand up.
It?
The volume
Yeah, will the volume increase or decrease?
increase
Increase?
since they're hitting the thing more.
Yeah. Higher temperature, higher kinetic energy, higher velocity. So now these particles will more frequent hit the piston, lifting it upwards, increasing the volume, but still holding the number of particles constant and the pressure constant. So that's a situation where we have a fixed pressure, fixed number of particles. All right. So how do we find the new volume? We want to find the new volume. So the volume increases. Find the new volume.
Is it just exactly the same as last time?
Is it exactly the same as last time?
Should be the pressure. Yeah, the pressure's constant.
Someone's shaking. That was how I asked the question. I put phrase ID into doubt.
Twist it, but yeah, you do the same, but you just flip the figures.
Because pressure is the same, right? So if you divide with pressure on both sides, they go away.
Yeah.
Number of particles,
And cancels.
they go away.
You're just left with V1.
So I'm just left with V1.
So V1 is equal to V2 times T1 over T2. Yeah, that's what I said.
Yeah, I didn't say you were wrong. I just said, were you right? That's a difference. Keeping everyone on the toes. So that just basically becomes exactly the same as this one here. So that means if I multiply with T2 to find V2, V2 becomes V1 times T2 divided by T1. So it's basically the ratio of the temperature that decides the new volume. Inserting the number 1.0 times 500 divided by 298, we get 1.67 decimeter cubed. So that is one way to kind of treat it, reading the question properly. What's fixed? What is being changed? And how will that affect the other quantities? All right, let's try to describe one more, and then you can try practice on your own. I draw now I have a container, I have gas inside the container. So they're randomly moving. Now I'm going to draw the change. What I'm going to do is I'm going to push the piston downwards. If I push the piston downwards, what do I do? What do I change when I push the piston downwards? Frey?
Decreasing volume, so you're increasing one of the other variables. So like
Pressure.
So I am
yeah,
decreasing
pressure.
the volume. But at the same time, I'm very clever, so I'm able to use ice cubes. You can imagine if it works or not. I don't think it will work pretty good, but it's my whiteboard. I decide it works. So I use ice cubes in order to hold fixed temperature.
At zero? Right, like 273 pounds.
No, the same as this one.
Which is?
Doesn't matter. For now. No, it doesn't matter.
Okay.
I'm holding the temperature
Then
constant.
it's the same.
Container is sealed, so that means that what do I mean when the container is sealed?
Fixed number of particles.
Yeah.
But fixed number of particles in the first one and the second one.
Hmm?
The fixed number of particles in both of them.
Yeah.
How can you decrease the volume if there's a fixed number of particles? Like
I
where
can
did-
just take, if no particles escapes, then
like more space between them, there less space between
Yeah.
them.
Just decreasing the distance between particles.
okay. So if I decrease the volume at a fixed temperature at a fixed number of particles, right intuitively, what changes?
Pressure.
Pressure. And what happens to the pressure?
Increases.
Increases. Yeah.
Yeah, inversely proportional.
And then we can use this formula here. That
The T goes away.
T and N and T, so that means that we have pressure times volume 1 is equal to pressure 2 volume 2. So the important, do you understand what happens to, so N, why does N go away? Because number of particles is the same. Why does T go away? Because the temperature is the same. So then I want to find the new pressure. So the new pressure becomes
A lot.
P2, then P1 times V1 divided by V2. Does that mathematically describe why the pressure will increase? Why will the pressure increase?
It's because you're decreasing the volume.
Yeah, decreasing the volume, so V2 is less than V1, making P2 bigger than P1.
So if you didn't have the ice cubes, would the temperature then increase?
Yeah,
Because there's more
Yeah.
kinetic energy.
that's a good question. That if we didn't have the ice cubes, you would assume both the pressure and the temperature would increase by pushing the piston together.
So would we have those several questions where two of them are increasing?
Yeah, you could get the question. That's why I kind of like to do it in this way, not the book. We start off with this. So if both the pressure and the temperature changes, you would just, then you have to use this formula here. Pressure 1 times volume 1 divided with T1 equal to pressure 2 V2 divided by T2, where only thing that remains constant is the number of particles.
Mhm.
Yeah. And if the number of particles isn't constant, then you have to use this entire thing.
Yeah.
So if you only have this on the data booklet, just divide PV with N times T, realizing that pressure times volume divided by number of particles times temperature, that will always be a constant. That's what I apply. And then read the problem, what are changing. Yeah.
Could we in theory say that if you divide the initial volume by the final, and if it's greater than 1, you know the volume is increased, if it's less than 1, you know the volume is decreased, and therefore you get sort of...
Yeah, there's different ways to solve it, kind of just understanding that if I reduce the volume by half,
Yeah.
I'm doubling the pressure. So there's different ways to solve that problem. Yeah.
Can you say when you increase the temperature, can you say that it also hits the surface with more force? Is that how you say it? Since now it's kind of moving faster, shouldn't it have more acceleration or velocity?
If the temperature increases,
Yeah, so then does the particle itself hit the piston with more force?
yeah, it exerts more a bigger force when colliding if it has a higher velocity.
So then the piston would rise up faster. If we're to have one at room temperature and one at like 300 Celsius, then the one with 300 should rise.
Yeah, I would assume so. Yeah. Because if you have a container wall and you have the higher the velocity or the change in momentum of both, well, technically it's technically the change in velocity that determines how big the force is. So the bigger the change in momentum, the bigger the force. Because the formula for force is change in momentum divided by change in time. But if we assume that all the collisions are elastic, higher incident velocity will also give higher reflective velocity, and so the change in velocity will be
Aren't you also
greater.
talking in terms of acceleration? In that you just described it in terms of acceleration, didn't you? Because you said
Because change in momentum is due to the change in velocity. Change in velocity over change in time is acceleration. But it's the acceleration during the collision. The greater the acceleration in the collision, the higher the pressure. Yeah. All right. So that is kind of ideal gas law. Explain what you need to know on the exams. And in chemistry you have learned, is it these words, Mariott's law? Is that something you learned in chemistry? You have done ideal gas in chemistry, right? You haven't?
Do you mean Boyles and Charles?
Boyle's law and Gay-Lussac's law, and you have
We have
done
not
those?
done this
Yeah.
yet, but we will.
Yeah. So in physics, I don't think those names are that important. You just have to understand that if you increase the pressure, volume, temperature can change. You have to read the problems, finding out what changes. All right. So
Okay, take a break. Are those the questions?
10 to, yeah, a lot of questions. 10 to 22.
Break before, please. It's been 1 hour.
Break before?
Yes, yes, yes. And then we'll ace those questions.
Yeah. I'll do a 10-minute break.